Weiss.
Hello.
Nice to meet you. Very excited to meet you because when I was younger, I studied some about digital audio processing, and maybe I ever want to be working in such a branch like you. But at last I go to work for broadcasting, for television.
Yeah.
So to me it's a very good and very interesting interview because I will solid my dreams, my younger dreams. I will at last meet a person who makes history in digital audio.
Yeah.
So thank you very much.
You're welcome.
I think that maybe the first question could be about your history, about what do you studied, where do you studied, what do you studied, how do you fundate Weiss, how was the beginning of Weiss, and then we can have some questions, some other questions. So when you want to start.
Yeah, okay. I have a bachelor in electrical engineering, and after studying that, I went to Studer Revox for 5 years. That was in '79. At that time, they started the PCM lab at Studer. So they started doing digital audio, and they had all new people for this lab. So this was a new lab, and we started at zero. Basically, we got some Sony digital audio stuff to study officially, and we did some A to D converters, D to A converters. Back then, it was a big issue. And I worked mainly on a sampling frequency converter, which is a huge box, and you have in a single chip several of those nowadays. But that was my main work. At some point, a visitor came to Studer and was asking for a specific interface from Sony F1, that was a digital audio recorder, to Sony 1630 or 1610, another Sony recorder.
Yeah.
So, and he asked us to do that, and Studer doesn't do such custom work, so I did it in my spare time. And this guy had a mastering studio in Germany, and it turned out that in this mastering industry there was a lack of having of digital audio processing basically for CD mastering. So everything was done still in the analog domain. So then actually we started the company together, or rather I had my own company. I started my own company, Weiss Engineering, and he had his Harmonia Mundi Acustica, was it called, and he organized for the sales of the products we eventually designed. So he knew what the market needed in terms of functions and interfaces and all that stuff, and I did develop this first product basically, which was a modular mastering system. So the customers were able to buy those functions they really needed. And also at that time the ASCII wasn't a standard yet, that was unknown yet. So they had all the manufacturers had different interfacing formats. So I did lots of different interfacing modules for JVC3M, SPDIF, no, not SDIF, the Sony Digital Interface, and all that stuff. So that was one main reason to do such a system. Then we added also like level control, equalization, dynamics processing, de-essing, mixing, all that stuff.
In digital or analog?
All digital.
All digital.
Yeah. So that, yeah, back then we had very few competitors because that was all very new. And at Studer I learned how to do such processors, basically. I mean, such signal processing, no such digital signal processing hardware. Back then there weren't any, well, there was one Texas Instruments signal processor, which was kind of available, but else you had to do it with discrete chips, basically, all the multiplication and summation, etc. So it wasn't that easy as it is nowadays, by far. It's, yeah. And then later on we did this Gambit series, 19-inch units, not modular anymore, but 19-inch equalization, dynamics, denoising, etc. And that we still do up to today. We started that maybe 25 years ago, but we still sell those units. It's kind of an indication for the quality of the units, that they are still up to date, so to speak. The limitation is 96 kilohertz in sampling frequency. But in studios, that's still okay, kind of, to have that limitation. In high end, you have the 192, 384, 786, and 768, etc. It's crazy.
And DSD? Have you ever made a DSD system?
No, I didn't touch DSD except for the sampling frequency converter software. We did Seracon. There is a DSD version, but only because we had to do it, kind of. The people were asking for it. I didn't look for that. You know, DSD you cannot process in the digital domain without converting to PCM and back again. So all those DSD recordings you get probably have been PCM at some point.
Yeah.
Or most of them. Nobody tells you that, but that's how it is. Also those D2A converters, there are lots of converters accepting DSD as an input format, but actually they convert to PCM at some point. And the purists don't want to know that. Yeah. In the year 2000, we started also, besides the Pro Audio line we started this high-end hi-fi line. So with a D2A converter, which we took from the Pro side to the hi-fi side by having a different chassis and nicer looks, etc. And so we started in the hi-fi line. Nowadays we are more in the hi-fi business, actually, in terms of revenue. So, yeah, we neglected the Pro Audio business a bit, actually.
But you have sell a lot of equipments in Pro Audio.
Yeah, sure, but not so much anymore in the last years, you know, because we didn't do new equipment. So the latest one was this analog 500 series amplifier. And it's already a few years ago we did that, and that's the latest one. And now we have this plugin from Softtube, which is our DS1 unit, compressor de-esser.
Then you program this plugin, or it's made by Softube?
Softube made that, yes. They took our DSP code. There are 5 DSP chips inside the unit, so they took the 5 DSP codes and translated it
to the plugin.
Yeah.
Okay, so it is quite similar.
Yes.
The code is the same, but there is no chips, there is no this DSP dedicated.
It's just a computer, yes.
Yeah.
Of course, it's not exactly the same because you have different floating point number formats in the DSPs and in the computer.
It is not the same.
It's not exactly the same.
I think that it is a very good question, because there is a war between people that think that it's the same to have a dedicated hardware or the plugin. What could you say about that?
Yeah, well, usually those people speak about having an emulation of analog units. That's a different thing, of course, because it's difficult, or can be difficult, to emulate an analog box, because of all those distortions and temperature-dependent behaviors, etc. So there can be a big difference, actually. Some plugin companies have a good reputation in having a good emulation, of course. But in our case, where we have a digital box which is transferred to a plugin, there you can have a much better, it's maybe emulation it's not the right word.
But could be the same?
Yeah, well, exactly the same. It's very difficult because of this floating point thing, You would have to do it probably in a fixed point or have the same number formats. It's not simple. But actually, I think it's not that important. If you have a null test with a minus 60 dB result, that's fairly good, I would say.
Yeah.
Of course, there are now discussions on the web whether it's the same. We have lots of customers having the DS1. They buy now the plugin as well and compare it. But you have to be very careful in comparison because the plugin doesn't convert to fixed point at the output because it's not necessary. You just feed the floating point to the next plugin or whatever. But in the DS1 unit itself, you have a conversion from the floating point to the fixed point with dithering added. So if you compare the two, you have to take that into account. So you would have to compare the fixed point numbers coming out. So in the plugin, you have to also take into account that you have somewhere a floating point to fixed point conversion, not in the plugin, but somewhere else. And that conversion you also have to take into account of the whole null test. So it's very difficult to do a proper null test.
Yeah.
Because dithering is involved and all that stuff. So. Yeah, it's an illusion to have a proper null test. But I think it's also not necessary. I mean, if you like the plugin, you don't know about the hardware. You like the plugin, that should be enough.
That's good.
Yeah.
Okay, and about converters, because you have several converters in the market. I think that maybe you are one of the persons that could tell us about the converters evolution from the beginning to nowadays technologies.
Mm-hmm.
It was a really evolution. For example, in the beginning, oversampling was used for conversion.
Not necessarily, no. No, in the beginning, I mean, I'm talking about audio converters. I think there wasn't any oversampling actually. I guess if we talk about A to D conversion, I think there weren't oversampling. That's why they needed these anti-aliasing filters, which were fairly steep. But of course, the difficulty is that you measure the A to D converter, say, and you would like to have good measurement data. But maybe it's not necessary to have such good suppression of aliasing, for instance. You rather would like to have a decent slope, so not a very steep slope of the low-pass filter you need, but a more better slope in terms of phase response. But then you compromise with the aliasing, But in the high frequencies, you don't have that huge amounts of level. So you're okay with some aliasing there because the level is already low anyway. So, you have to know about those compromises you are allowed to do, kind of.
Mm-hmm.
If you don't care about measurements, but you care about the sound, So if you care about the sound, you're allowed to do such compromises that you have the slope different and allow for aliasing, but have less phase issues.
Could you, in brief, give us the highlights of the evolution of the converters?
I don't know whether I know enough. Yeah.
Maybe the highlights only. When was the oversampling used? When was the clocking be very interested to take care?
Yeah, well, that was from the start, of course. The clocking was extremely important, or is extremely important, so we don't have any jitter effects. But I don't know when this oversampling or sigma delta scheme came up in audio. Well, it's years and years ago, of course, tens of years probably. But this is what's used today, basically. Most converters are sigma delta, null shaping converters. Yeah, at some point they used this 1-bit. You remember the CD players with the one bit writing on the front panel?
Yeah, from 2.8 megahertz.
Yeah,
with 1 bit.
That's what DSD is coming from, this 1-bit converter. The DSD started because of that. They use this technology, but they don't use that anymore for a good reason. Because the advantage is that you don't get any distortion because of the quantization non-linearities. But the disadvantage is that you get some idle tones, which are very difficult to tame, so to speak.
Mm-hmm.
That's the disadvantage of this 1-bit thing. And nowadays, the sigma deltas are multi-bit, like 4-bit, something like that, or maybe even more, 6-bit, I don't know. But a few bits in any case, but at high sampling rates, of course. So that they have, obviously they have some advantages. That's why they do it nowadays like this. And DSD is still with us, with this 1-bit compromised format, basically. Of course, people like, lots of people like DSD. I don't mind, of course. Mm-hmm. But from a technical point of view, it's old-fashioned, kind of. But if it sounds okay.
If people is happy, go ahead.
Yeah. It's like with the cables and all that stuff, this.
Yeah. The hi-fi world of buying a 200 euros per meter cable.
Yeah, or even more. But of course, that's a drawback, that there is some rip-off involved often in those things.
If you are happy, go ahead. So we were talking about clocking. Maybe clocking is one of the most important things in digital world.
Yeah, sure. Yeah.
What could you tell us about clocking? How do you develop your clocking systems? How do you manage the clock? Because you need to have a very stable clock to do the all the conversions and maybe the processing. What could you tell us?
Yeah. One thing I see is those 10 megahertz rubidium clocks. They sell it in studios and in high end as well. But that's actually a bad idea, because they are very stable. They are extremely precise. So you get your 44.1 kilohertz extremely precise. But that's not what you need, actually, because if it's off like some ppms, or 10 or 20 ppms, which is already a lot for a standard clock, parts per million, so that's not important. You get a slight pitch variation, but it's so small, and so the precision is not really important in digital clocks, except maybe for satellite things and such.
Yeah.
So, but in normal audio, that's not important. It's more the jitter behavior. And with those 10 megahertz standard frequency generators, you have to do a conversion to standard audio sampling rates, which means you have to put in a phase-locked loop converter, which introduces jitter by definition, basically.
Yeah.
It's an analog circuit. Usually it can also be digital, but a good one is usually analog, and that has some noise, etc., and which introduces jitter. So in that respect, it's better to have a crystal oscillator. There are different ones, of course, in terms of jitter, etc. But a basic crystal oscillator as the source for sampling frequency generation, and get much better jitter. Not the precision of those rubidium clocks, but much better jitter, I would say.
It is better to invest in a good phase-locked loop?
Yeah, actually, in that case, you probably even don't need a phase-locked loop. I mean, if you have a crystal at the proper frequency, you need. And well, with a 10 megahertz clock, you would have to invest in a good phase-locked loop, yes,
yeah,
to get that better. Yeah.
But there are not actually crystals or quartz in 44.1.
No, but multiples of it.
Yeah?
Like 22 point something megahertz.
Is there?
Yeah.
I don't know.
Yeah. Or multiples of 48 kilohertz as well. So those are standard. And crystals you can order to any frequency, actually, if you are ready to pay some decent amount. Mm-hmm. But that's possible. But those 44.1 multiples are standard frequencies nowadays.
What is the most difficult to design in a converter, analog digital and digital analog? What is the main source of problems?
Yeah. Well, I'm talking about those designs which are based on a chip, on an A to D or D to A chip, which takes a lot of work already, you know. You could also do your own converter with transistors, etc., which is another thing. But if you take, say, a standard A to D or D to A converter chip, then the difficult things are the clocking, yes.
The clocking.
To have a decent clock which is properly fed to the chip, of course, without any noise interferences and so on, ground things, you know, ground noise, etc. And then, of course, usually those chips have a D2A chip has usually a current output, not a voltage output. So you need a current to voltage converter, and that has to be properly designed as well to cope with the high speed output edges from the converter, because the converter has like this step-sized, step-formed output currents, which have very high frequencies, of course, included, which you want to filter out. And so the current to voltage converter has to be able to cope with those steps, so to speak. Yeah. And of course, yeah, the power supplies is also important.
The power supplies you use, switching power supplies, linear power supplies, both.
Yeah, both actually. You know, I think the switching power supplies have not a good reputation, but actually they can be better than or at least as good as the analog power supplies, I would say. If you have the radiation under control and all that stuff. But in terms of quality of the output voltage, it can be very good.
But it can induce some noise in the electrical wires.
Yeah, of course. Of course, you have to take care of that. Also on the primary side, on the input side of the switching regulator, you have to take care that it doesn't feed back to the source. Yeah.
Can induce some noise with the transients of the power supply inside the analog circuit.
Yeah.
Because it is radiation.
Yeah.
By air or by wire.
Yeah, both. Yeah.
Actually. And how do you manage it?
You have to do some decent filtering and maybe even an additional stabilization. That's what we do. We have, say, a secondary switching power supply. Secondary means you have a normal analog transformer, mains transformer, then the switching power supply to get the voltage to slightly above the voltage you need in the end. So say if you need a 15 volt power supply, for instance, you regulate down to 16 volts, say, and have the last volt regulated by an analog regulator, which this scheme has the advantage that the power loss is not that high. The power, the efficiency is fairly high because of the main step you do with the switching regulator, which has a high efficiency, like 90% and above.
Mm.
And the last volt you do with the analog regulator, which then only has a small voltage to kill. So I think that's a good scheme in terms of efficiency and low noise on the power rails.
Mm-hmm.
You don't believe that?
I believe. Uh-huh. Because I studied both systems and I know how it really works. But maybe I have some doubts about the noise, the induced noise, because the transients are very can spread over the cables in the air. So I think that you need best filtering that in with linear power supplies.
Yeah.
Because if you have a voltage regulator, a chip with voltage regulator, it is very stable and there is usually a very low noise. It's a very low noise source. But the transients, you must have a very good filtering system to not induce noise in other equipment.
Yeah, but you don't usually you have like your processor board, which also has very high transients or fast transients on the power supply. So that's the same issue. Even if you do an analog regulator power supply, you still have the same problems because of what you're feeding the power to, all the processor things.
And about processing, because just we talk about converters, so now I think that maybe processing is some questions about processing. You have two kinds of equipment. You develop equalizers and compressors, and other kind of processing.
Yeah, we have also in this Gambit series I mentioned, we have also a DNA1 unit, which is denoiser declicker unit for restoration. So, but it's all based on the same DSP section, no? The EQ, the dynamics, and this denoiser. So it's just a matter of software then, basically.
when you design, for example, an equalization, you made FIR filters or IIR filters?
It's actually, we have different versions of the EQ1. We have also linear phase unit, which you would think it's an FIR. Well, it's an FIR.
Yeah.
No, it's not an FIR. Actually,
Linear phase is FIR.
yeah, it doesn't need to be actually, because you can.
No? You can achieve a linear phase with an IIR?
Yes.
Really?
But not with an ordinary IIR. You can have two IIRs in series, but one is reversed.
Ah.
So linear phase is when you have a symmetrical impulse response, as you know.
Yeah.
So in order to get it symmetrical, you have to reverse one of them. And then you get this symmetrical impulse response, but you use two IIRs in series. And the advantage is that the DSP power you need is much less compared to an FIR, the standard FIR. That's the main advantage.
You need less coefficients and retards.
Yes, but you have two in series, so you have to take that into account when you calculate the frequency response and that stuff.
And you design in the zeta plane. You go to the circle. You put the poles and zeros over the circle.
No, well, that was an engineer doing that. That was not me myself. But no, do you have? Actually, we have a standard because we do the filter design in the unit. When you turn the knob, then the filters are calculated coefficients on the fly. Because that was our first design. We had tables with all possible in a one band parametric EQ. You have boost cut, frequency, and the Q quality factor.
But so you have a machine that calculate the poles, the zeros, and draw the zeta plane?
Yeah, it calculates the coefficients for a biquad filter. Basically, it's 5 coefficients.
But with a machine or writing?
The DSP does that.
You really?
When you turn the knob, it calculates that on the fly. So,
when I was young, I used to have the transfer function the Laplace and made a lot of calculations.
Yeah, but the drawback is if you do that, if you have three parameters on one band, you have thousands of different settings, you know, and that is a huge table in the end. We did that, but we had only a few Q. We had only 5 values, for instance, or so, 5 possible steps to have a smaller table. But later on, we had 128 steps for all parameters. So we had to do some real-time calculation. And in the dynamic, we have also a dynamic EQ. And there, the frequency response is changing with audio. And the coefficients are calculated on the fly during the audio changing. So it has to be very quick.
Very, very quick.
Yeah, but it's possible. And we have also, we don't have the ordinary bicode
I think that
architecture.
I must have one of them in my exams. It could be very easy. So, in brief, which are the steps? What are the steps in audio processing design? For example, do you have ever made some calculations? You need to calculate the transfer function.
Yeah, well, of course, it depends on what exactly you're designing. But basically, it depends. But if, for instance, the EQ, I would first, when I don't have any idea about an EQ, then I first go to look for some literature on the web and see what is possible, and also looking more in the problems, like it's not the normal form backward architecture of an IAR filter. That's very sensitive to the precision of the coefficients. And so that's especially at low frequencies, low corner frequencies. So that's a drawback. So you would look for a solution to that. And then you see other architectures which are more complicated, but which are not sensitive or not that sensitive to those things. And so, if you try to do it as good as possible, then you end up at such things in the end. You don't use the normal cookbook EQ thing. That would be simple. It's the first thing you will see in all textbooks. But if you don't like the problems, and if you think there should be less noise at the base frequencies, there must be a solution. Then you will end up with more complicated things, and that's maybe the important thing to do. That you're not happy with the first approach usually. You should have several steps, or
several trial and error.
Yeah, and never be happy with anything. That's maybe the credo,
And how is a compressor processing made? Because in analog domain, you have a side chain for comparing with the input signal, but in digital, how are them developed?
Yeah, it's the same actually. It's the same as in analog.
With a side chain?
With a side chain and lock, anti-lock calculation and threshold comparison and ratio. So the advantage in digital is that you can have a delay. So you can look in advance what's coming.
Look ahead.
Look ahead, I mean, yeah. Exactly, and in the analog that's very difficult to do. Close to impossible, I would say. There are some analog delay lines, but they are noisy like crazy.
Yeah.
So that's a big advantage, to some point. Of course, you can do a sound with the analog. But some specific things you can't do in analog in terms of compression. So you can't catch a peak right away. You're always too late, so to speak.
Yeah.
Analog. It's difficult. Yeah.
And in terms of programming a DSP, you use assembly language
Yes.
or maybe C++ and then
No, we always use assembler.
assemble.
Yeah, because of course it's much more difficult to do that, but it's the most efficient code you can get in the end. And we use the Sharp DSP from Analog Devices, and those are very good in terms of programming complexity. They're not that complicated. I had different earlier on. I used the DSP32 from AT&T, the first floating point DSP, and there you had to take care of things. Like some results were available 4 steps later. You have to know that, it's not before. So because latency of those different calculation entities. So yeah, crazy. But so the short and modern DSPs are much better in that respect.
And why do you choose the analog devices DSP? Because there are others from Texas Instruments,
Yeah,
Motorola. Why do
Yeah.
you choose analog devices?
It was somehow appealing. I don't know. Well, maybe actually the first one we used from Analog Devices was the 21065. That was the first low cost, they called it, low cost DSP, which was really low cost actually, but still powerful and floating point, and so that was an appealing processor. Nowadays it's very old, of course, but we still use it in the EQ1, 5 of them.
Yes.
But one single modern one is replacing tons of those. So, in terms of DSP power.
Yeah.
Yeah.
When you are developing a new algorithm inside your DSP, you have the classical miniature DSP with a DSP, some ROM, RAM, with the power supply, and you test connecting it to the computer, and you have such kind of devices that there are sometimes in schools and universities.
I mean, so demo.
Yeah, demo board.
Yeah.
You use that's such devices to test your products.
Yeah, to some extent. I have one here in this box there. You see, there is a DSP board in this cardboard box, this blue one there.
Ah.
There is a DSP board inside.
There is no Sennheiser.
No, it's not. It's an Analog Devices board.
Yeah.
And I use it for testing some algorithms, which Analog Devices has a programming surface with block diagram based programming surface, which is very convenient. So it's very simple to do with all kinds of filters, etc. that I use. But else, that's the only one we got for that purpose. Else we do it right away in the hardware. We first have to design, of course. So we do first the hardware and then the software, without going through a demo board thing.
Mm-hmm. And all your plugins, all your DSP, because plugins you don't programmate you.
No.
All your DSP use floating point.
Yeah, mostly, yeah. There are some things like tethering you have to do in fixed point.
Why?
It's difficult in floating point, maybe even impossible. I'm not sure, but yeah.
Why do you really need such precision, such accurate, to use a floating point?
Yeah, the precision is not the issue. Well, it's an issue. No, it's more about this dynamic range. Especially, well, EQ is not such an issue, but in the dynamics processor, you like to have a huge dynamic range because you need those log anti-log calculations, which can get huge values. Like, yeah, the dynamic range with a 32-bit floating point format, you have 1,500 dB dynamic. So that's a lot, 1,500 dB. So you can have huge levels without, without problem.
I never know a man that puts 40 dBs in an equalizer.
Yeah, but in dynamics processing, you can get large numbers and then small again, and so so it's just very convenient to program. That's that's the main reason basically. Fixed point, you have to take care of the scaling all the time, that you don't underrun or overrun the format you have. And yeah, you have to take care of the proper levels all the time, so you don't go outside of the range you have. But in floating point, you don't care about that.
Yeah.
Basically.
And about sampling frequency and bit depth that are today maybe 96 kilohertz and 24 bits. What do you think? We really need such kind of sampling rates and so many bits?
Yeah. Yeah, actually sampling rates there are some people discussing that all the time, of course. But one number is like 64 kilohertz or so, which would be ideal from sonics and from DSP power required
64.
for processing, like about 60 kilohertz or so, something like that. So in that, more than 48 is a little bit, of course, it's good enough for 99% probably. But still, you can say, okay, 64 is, once we have that, we are okay. But we have 96, for instance, so 96 would be okay in my opinion.
But this is in terms of DSP managed, because the converters use oversampling. You are talking about the more information you have, the more accurate in the DSP process? Or why do you think that 60 kilohertz?
No, because of the frequency response you get.
Yeah, but in the conversion or in the DSP process?
In the DSP process,
Yeah.
if you have some non-linear processing, then you generate harmonics, which can be quickly above Nyquist frequency, which is half the sampling rate, and get LA'd. So that's maybe one reason to have a very high sampling frequency if you have non-linear processing. But usually you don't have that, except for maybe if you're simulating a tube or tape, or some non-linear process. But there you have to take care that you don't have such high harmonics. So then you can also run at ordinary sampling rates, like 96 kilohertz or so. You just take care that you don't generate harmonics above 48 kilohertz in that case, and then you're fine. But that would be one reason to go higher in sampling rates. But else, I don't see a reason. Of course, people say that you have nonlinear behavior in the ear when you have high frequencies above 20K, for instance, and that you can modulate down to some frequency you can hear, all that stuff, But then your speaker would have to be capable to reproduce like 40 kilohertz or something as well. I mean, else there is no point to go to high sampling rates. And nowadays, 192 is already standard. I mean, they want to have that, and 384. Our latest D2A converter can handle 384. We did that because the chip is capable to do it. So, but it's kind of crazy, It's, yeah. And we have to talk. Of course, we have to differentiate between the Pro-Audio and the high end. The high enders are crazy. They like to go as high as possible.
Yeah.
The higher, the better. That's the basic idea.
Yeah.
Of course, it's not true. And the Pro-Audio people are more down to earth.
In the war.
Yeah. So lots of them work at 48, for instance, or 44.1 even, and they're happy with it.
And did you ever thought, for example, when you have a PCM stream with 24 bits per sample, the internal DSP processing transform it into 32 bits, fixed or floating point? Did you ever think to upsampling the input signal to process?
Mm-hmm. Yeah, actually, in this latest DDA I showed you, which has a DSP inside. Actually, we do a conversion to 195 kilohertz inside that unit.
So you are doing an upsampling.
Up or down sampling.
Up or down?
With a 384 input, we downsample basically to 195.
For DSP process
Yeah,
purposes?
The DSP processing is done at 195, and the DDA converter itself is running at 195. So that's a secret. That's how we do it in that unit. Of course, it's simpler to handle the whole DSP stuff at one single sampling rate. Else you would have to switch the coefficients and everything depending on the sampling frequency. So we decided to have a single sampling frequency, and we decided to have that fairly high, not something like 96 or something, but fairly high, and run the DSP at that rate. So it's kind of a compromise between the high-end people asking for high sampling rates and our thinking about high sampling rates. So, yeah, and also the DST input is converted to PCM to 195. So, yeah, that's how it is.
You produce some equipment to do upsampling and downsampling purposes only?
Yeah, we do that, yeah.
And what are the traits or when you are designing such kind of equipments? Is there some problems when you try to translate, for example, in not multiplies? Is there some problems when you need to do some upsampling, downsampling?
Mm-hmm. You mean between arbitrary frequencies?
Yes, because when you have natural multiply, it is easy. But when you need to manage with different and not multiply, you must to do sometimes upsamplings, then downsamplings. You need to accurate.
Yeah, actually, that asynchronous converters, we haven't done any. That's what you mean, that you have kind of independent clocks, input-output. So we have an arbitrary ratio, and that we haven't done, actually. We only have done synchronous designs. So we have a factor which you can express with a nominator-denominator, a ratio, yeah. So you have to go up by a factor, integer factor, and go down by another one, like 44.1 to 48. You think that can be related, but there is 160 times 44. 1 is 147, I think, times 48. So we have a ratio of 160 to 147.
But the iteration, when you are doing an upsampling, you are adding some zeros, then you are convolution. And it is easy if you, for example, once twice, because you put a zero inside between two samples. But when you are not a direct relationship, you must do some upsamplings, downsamplings to achieve the correct value.
Yeah, but you can do that in one step. I think the most effective way is with the polyphase, so-called polyphase filter, which means that you have the zero filling you mentioned, and then that's the input. So you zero fill the input depending on how high you go with the sampling rate. And then you take, for the output, you take only those samples you really need at the output. So you don't calculate all of them, like the 160, like the factor 160 times 44.1. That's 7 point something megahertz. So you don't calculate the whole filter at those 7 megahertz, which would be a huge DSP power requirement. But you only calculate the actual output samples you need, the 147 lower sampling rate, factor 147, like 48 kilohertz. So you have to take the proper selection of those zero-filled input samples and coefficients, of course. The filter is maybe 20 or 30,000 coefficients long, the filter, the FIR. But you only need a few coefficients out of those 30,000 for each output sample. There are books about this method. So it's very efficient, in terms of DSP power.
Yeah.
You need lots of memory because of this 30,000, for instance. You have to calculate the coefficients, 30,000. But actually, afterwards in the processing, you need only a selection of, say, 100 or 200 per output samples.
And you have the same accurate when you goes from an integer number than when you need a lot of decimals.
Yeah.
The same quality and the same accurate.
Yes. Yeah.
So today is not a problem to do an upsampling or downsampling.
No, because 44.1 and 48 and multiples are kind of related, nicely related. They are not that way off. 44.056, which is the NTSC-based sampling rate. That's different, I think. I don't know the factors there, but 44.1 is not too bad.
And about dithering, I think that maybe every time you make a new quantization, you need to use a dithering. Your DSP codes implements dithering in all requantization times?
Yeah. I don't know, because we are using floating point. I don't know whether it would be good to have dithering in there.
Yeah, but
Probably not.
when it is fixed,
If it's fixed point, yes, you have, when you requantize to a lower word length, then you should apply dither, yes. But then in our case, that's only the case at the output of the unit. When we go to ASC view format, for instance, with 24 or 16, if you go to CD format like 16-bit, then that's only at one place you have to add the dither. So it's not too bad.
is there differences in quality when you program a DSP or you use a native computer?
No, I don't think so. I don't think it should be different, provided you have the same algorithm and a decent floating point resolution, etc. But don't think it should be any different. So I know people are thinking that the hardware is better than the software, so to speak, but both is software.
How do you think that will be the future of digital audio processing and digital audio in general?
Yeah. Yeah. Difficult. You mean in terms of functions or how the hardware looks? Or well, of course, there are much more powerful processors available. So what the workstation is doing nowadays, that was a supercomputer a few years ago, almost. So yeah, it's much easier to do more complex processing. But of course, the difficulty is to program those things. In terms of computing power, we have lots of power available. But to make things which make sense, it's a different thing. And probably you're asking about those things, what kind of functions we would see or would like to see. Or
Maybe better DSP to get more power?
Yeah, there are already DSPs, or you can add DSPs because they are so cheap, and so that's not an issue. The DSP power is not an issue anymore. It's more to have an actual algorithm which helps the pro audio people, for instance, to process audio. Yeah. Well, because we are doing now the speaker, as you have heard.
Yeah.
There is, I think there will be lots of change in audio regarding the virtual reality, augmented reality stuff, because this will ask for audio which we don't know yet. Because, if with the 3D goggles you may have also tested, or you maybe own, you see the picture is crazy. The 3D picture is like crazy. And the audio which you have usually in your headphones, it's a joke compared to the picture.
Yeah.
Isn't it? So, because if you see the dragon back there roaring at you, you would like to hear the roar coming from there.
Yeah.
And not from inside your head.
Yeah.
So there will be high demands on proper audio for 3D or for virtual reality stuff. So, and there are lots of companies working on that, actually.
Okay, I think that we have so many information I will spend hours, days, weeks, and months here speaking with
I don't
you.
hope so.
But I think that you have, I get a lot of time of you, and you want to be back to your work. So I think that we will see your facilities now. A little tour to see the facilities. I'm very happy to be here today.
Yeah, thank you.
So thank you very
having
much.
me. Thanks.